for the first speaker of this section. His session is Yael Shadmi that will tell us about amplitudes for SMEFs.
Thank you. So thanks very much for the opportunity to be here. So we're back on the firm footing of helicity amplitudes for this. And I will talk about amplitudes for standard model EFTs. This is work done with this excellent group of students and postdocs. And specifically, what I want to talk about is EFTs for electroweak symmetry breaking. So we have a very simple parametrization of electroweak symmetry breaking using the Higgs mechanism with this well-known potential. But really, this is something that is very ad hoc, and we sort of put it in by hand, even though this is the simplest possibility and therefore nice and elegant. Still, there are many things we don't understand about this. Why is there a minimum away from the origin? Why is the symmetry broken? What sets the scale to the value that it needs to be? And why is this stable against radiative corrections? So for the sake of those of you who were born in the 90s, let me remind you of at least one example of a weakly coupled theory that can give a dynamical explanation of this type of behavior. And I'm talking about something weakly coupled because certainly we don't see any signs of strong coupling at this point at the LHC. And this is generic supersymmetric extensions of the standard model where the stop mass plus the large top Yukawa drives the Higgs mass squared away from the origin and give you this minimum away from the origin. And there's also an origin of the scale here, which is precisely the new scale that's required for dynamical supersymmetry breaking. So this is just a reminder that, yes, we can have dynamical explanations of this thing, but at this point, we don't see any of this. And we haven't made that much progress either because we know that if there is such a thing, it's tuned at the level of maybe 10 to the minus 3, 10 to the minus 4, but that's still not enough to give up on naturalness. So this is where we are. And this is why we've been talking so much about EFTs for extending the standard model beyond the Higgs. And if you think about it, EFTs and electroweak symmetry breaking go back a long ways. The first sort of prototypical EFT that we know is associated with beta decay, where we've seen the footprints of the massive W and therefore part of the Higgs. And now we're back to EFTs, trying to understand what's really happening beyond this naive picture that we have in terms of the Higgs. So to construct an EFT bottom up, you usually start from the most general Lagrangian in terms of the standard model fields. You write something that's consistent with all the symmetries, the global symmetries and the gauge symmetries. And this involves a bunch of Wilson coefficients Ci. But you can do exactly the same thing on shell. Here you start with the standard model particles, and you write down the most general amplitude that's consistent again with the symmetries. And there is a one-to-one correspondence between the Wilson coefficients appearing here and the couplings appearing in this amplitude here. Now, from the point of view of experiment, we're really in a period of physics heaven, if you wish, because there's a wealth of data coming from the LHC, and we're just beginning to scratch the surface. This is where we are roughly in terms of integrated luminosity, and we should go by the end of the LHC program to 3 or even 4 inverse Erdobarns. And so the question is, how do we interpret these data in terms of the standard model plus any possible BSM? So of course, one thing that you need here is precision. You need to compute standard model predictions very, very precisely. If you wish, this is in the category of known unknowns. But then there's also the possibility that there's some new effects that you're not aware of, and you need to look for them and sort of parameterize the unknown unknowns. And this is where effective theories come into play. So we're talking about a very complicated problem. There are many, many measurements, and there are many EFT operators that come in. So just to give you an idea, at the dimension 6 MEFT, there are 1,000 operators, or about 100 if you restrict to one generation. When you go to dimension 8, there is a factor of 10 more. And this mapping becomes very, very intractable. So one hope with Amplitudes is that it will give you a more direct mapping between the theory and the data. Okay, so when you bootstrap Amplitudes, you of course recover the standard model amplitude and rediscover things that you know about QFT. And you also get the most general EFT amplitude. And the nice things about this is that it's model independent. There are no issues of field redefinitions, coupling redefinitions, and so on here. So it gives a very natural approach as we try to go beyond the standard model. And it's given directly in terms of physical quantities. So it can give you some handles on constructing sensitive observables to pick up certain contributions. So let me talk a little bit, though, about this part here. One thing that's by now a standard QFT textbook example, thanks to the book by Matt Schwartz, is how spin-1 interactions really dictate the structure of Lie groups and how the two are related. And let me give you the massive version of that very quickly. So there's a kinematic part, a Lorentz part that's completely antisymmetric, which tells you that this coefficient here needs to be completely antisymmetric. And of course, this is consistent with the structure constants of Lie groups. And so we really see the power of Lorentz in dictating this. Another example that I want to talk about here today is related to the Higgs mechanism, as pointed out originally in this paper, because this is going to be playing a big role for us. So the plan is I want to talk a little bit about the anatomy of the Higgs mechanism at the amplitude level, and then we'll apply this to on-shell derivations of EFTs. So we'll start with this on-shell Higgsing, and my main focus is going to be the contact term amplitudes, and in some sense this is unifying these two early works on the subject. So here I want to start with the massless amplitudes of the unbroken theory, and then Higgs these on-shell to get the low energy massive amplitudes. So here is some amplitude with lots and lots of extra Higgs legs that you can barely see. And when you start looking at that, you're really starting to probe field space. And what I want to do here is I want to take these guys to be non-dynamical, so we want to take their momenta to 0. So from this, we can read off the massive amplitudes essentially by matching them at energies that are much higher than these Qs, which I'm taking to be of the scale of the masses. And the assumption here is that there is a single Higgs and therefore a single VEV, and all the masses are essentially the same scale. So then the low energy amplitude is given by a series expansion in this VEV of amplitudes with more and more Higgs legs. So the first thing that happens is that the massless spinor structures associated with this amplitude get bolded. So let me give a simple example of how this works so that it's something concrete. So here, for example, is an amplitude with a vector leg of momentum k. So it comes with this factor. Because we assume that there is a gauge coupling here, there is also another n+1 point amplitude in the theory that factorizes in the limit that q goes to 0 on this original endpoint. And we need to multiply that by v to get the correct dimensions. So all in all, when you add these things up together, you get exactly the amplitude with a massive vector coming with this massive spinor structure. And so what you're seeing here is that this soft Higgs leg supplies the second light-like momentum that's required to form a massive momentum out of the original massless one. And the symmetrization over little group indices comes from just exchanging these two Higgs legs here. So the spinor structure, the massless one, just gets bolded, and that's very simple. And again, we're seeing here the power of Lorentz. The Higgs mechanism and Lorentz symmetry are completely tied together. And from the point of view of Lorentz, what's happening is that bolding the massless spinor structure is essentially covariantizing with respect to the full massive little group. So in terms of what happens to contact terms, it's very easy to see what's going on. A massless fermion and a massless vector leg just get bolded. A massless scalar with the momentum insertion pi gives rise to two low energy amplitudes, one that corresponds to another massive scalar with a momentum insertion pi, or it can also give rise to a contact term with an external vector leg where this vector just gets bolded. So we see exactly how the longitudinal vector arises from the Goldstone boson. The other thing that happens is that couplings get order V corrections. So here is this low energy coupling, and it's getting corrections from all of these higher point contact terms. Okay, another example that I want to mention very quickly of sort of rediscovering standard model stuff is the relation between gauge invariance and perturbative unitarity. So it's well known since the 70s that if you want to extend the standard model in a way that preserves perturbative unitarity, the only way to do this is with a standard model gauge group. And this relation becomes really, really transparent when you work with amplitudes given in these in terms of these little group covariant spinors. So here, for example, is an amplitude with a W leg. So it comes with this vector. And the problematic terms are the ones that involve this polarization, where there is a factor of m in the denominator. And then looking at one component of this tensor, you get e squared over m squared behavior. Looking at another component, you get this factor of P1 spinor divided by m, which is finite. So you get some dependence on something, some finite spurion that's completely spurious, some finite spinor that's completely spurious. And therefore, the fact that the cancellation of bed energy growth is completely equivalent to the cancellation of the spurious dependence. And what the spurious dependence is really the reference spinor associated with the massless vector. Okay, so again, we see here the power of Lorentz. So now let's move to EFT applications. So this field has grown very, very quickly, and there are lots and lots of things that I'm not going to have time to go into. And the thing that I want to concentrate on is the following. In many of these, what you do is you use the amplitude to say something about the Lagrangian. But at the end of the day, what you really want to do, what you need to do to go to experiment is go back to the amplitude and then turn to experiment. So I just want to look at this arrow here, the direct connection between the two. Okay, so there are different EFTs that you might be interested in. You can consider EFTs that have just the standard model particles or some new light particles. You can consider the SMEFT, which is the main thing that people have looked at, which has the full gauge symmetry of the standard model at lambda. In this case, to construct this, you need the massless standard model fields. The Higgs is, of course, in a Higgs doublet, and so on and so forth. And there is a large-scale separation possible between the EFT scale lambda and the VEV-V. If you don't do that, then you only impose SU3 cross C1 at lambda, and then you treat the W, the Z, and the Higgs as independent degrees of freedom, and this gives rise to what's known as the HIFT. In this case, the full symmetry is realized only linearly, and there's no scale separation possible between these. And these, a lot of these things were stressed recently in a series of papers by these people. So in the SMEF, to derive predictions, there's a number of things you need to do. You need to find the basis of operators and the unbroken theory. You need to turn on the Higgs web. As a result, the Lagrangian becomes shifted, gets shifted. Both standard model fields and their couplings get shifted. You derive the Feynman rules in this broken theory in some gauge, and then you redefine parameters from some input physical masses or couplings. And working with amplitude saves you a lot of those things because you're working directly with the physical degrees of freedom. Going on to the heft, in some sense, this is really a sick EFT. For example, you've integrated out some fields which get their masses from electroweak symmetry breaking. So there can be no scale separation between lambda and V. Also, the UV matching is, can sometimes be ambiguous, as these people showed recently. And amplitudes make a lot of this concrete. So let me start with the bottom-up construction of amplitudes. So here you want to start with the massive and massless particles that we know and construct the most general amplitudes. So the first step here is to construct the most general 3 points. These include both the renormalizable and higher dimension ones, and these are dictated by the symmetries. Then these determine the factorizable parts of the higher point amplitudes, and then you need to supplement that with the higher point contact terms, which are again dictated by the symmetries. So this is what it looks like. So the contact terms are just the structures that are manifestly local. There are no poles. This here contains a bunch of spinor products. It carries the little group weight. And we've stripped it off of all the Lorentz invariants Sij. So we refer to this as an SCT. And this here is a polynomial in the Lorentz invariant subject to some kinematic constraints. And so this is essentially capturing the derivative expansion in the Lagrangian. So since this is a completely bottom-up construction, with the input being the physical particles and just this symmetry, and in particular the Higgs is a gauge singlet, this gives heft amplitudes. What about getting low energy SMEFT amplitudes? Here we can use on-shell Higgsing. So here we can construct the massless amplitudes associated with the full gauge symmetry, and then Higgs these down to get the massive amplitudes. So let me show you some results. So there's a whole inventory of results for the heft by now. I'm going to concentrate on this here. So in this paper, we derived all the heft 4-point contact terms up to dimension 8. Of course, this is the natural first step because this is the most relevant for collider studies for 2-to-2 processes. And the counting of dimensions is very simple here because you can just classify contact terms according to the energy growth. So for example, if you're interested in terms with E² energy growth, this is the full list of them. And mostly these correspond to dimension 6 operators. So what these products here are either square or angles. The C's are different Wilson coefficients. And here we have directly the low energy contact terms. Similarly, we also derive the full set of contact terms with E³ and E⁴ growth. And these correspond to dimension below 8 heft operators. There's a clear identification here of the operator dimension from dimensional analysis. So what you need to remember is that factors of squares and angles for external massive vectors come with a normalization of M. The most immediate way to see this is by the fact that this is just the massive polarization vector for these guys. And then any extra powers of E are compensated by powers of lambda, and that allows you to read off the dimension of the operator. But in some sense, this is kind of moot because recall that lambda is sort of the same order of V in this case. And in some sense, this E over V behavior really reflects the non-locality of this heft because there are some things that you sort of integrated out that you shouldn't have. Okay. Now this is the same list for the SMEFT 4 points at dimension 6. So the way we got them is to write down the full list of massless amplitudes at dimension 6, and then Higgs these to get the massive amplitudes. Now, there's also interest in going to dimension 8. Dimension 8 operators have been shown to give interesting effects in different contexts. For example, I'll tell you why they're interesting here. This is, of course, a real mess because there are many, many operators, as we said. But if you're thinking about amplitudes, then it's very easy to concentrate on the ones that are relevant for the process that you're interested in. So the example that we've looked at is we're looking at, is the pair production of two Ws, two Zs, or any gauge bosons, because this is a sensitive probe of electroweak symmetry breaking. And so it turns out that all the relevant 4-point contact terms are first generated at dimension 8 in this case. The dimension 6 SMIFT, all it does is to correct the 3-point couplings. And it's very easy to see this just by counting dimensions in these amplitudes. So we derived all the low energy 4-point contact terms that enter in VV to VV, or fermion pair to vector boson pair. And since we're keeping the vector masses here, these kind of resurrect any vanishing interferences between the standard model and the EFT. They're also good at intermediate energies, not just at the very high energy tails of distributions where the EFT really fails. They're sensitive to anomalous Higgs couplings, and at this order, the degeneracy between up and down coefficients coming from SU2 is broken for the first time. Another thing this allows you to do is to distinguish between the HEFT and the SMEFT. So, of course, you have various couplings relations implied in the SMEFT, but also there are some SMEFT zeros due to hypercharge or completely accidental. Okay, and as I said before, this is the structure of these terms. So this part here depends on the scattering angle and the decay angles. This just depends on the scattering angle. And so once you have the form of these new structures, you can think about constructing observables that would isolate the new effects which don't appear in the standard model. So this is work in progress with Stefano here and these other guys. Okay, another last thing that I wanted to describe very quickly is another work in progress where we try to rephrase electroweak precision measurements in terms of these amplitudes. And so in the case of LEP measurements, a lot of the observables have to do with 3 points, with pole observables. So these are very simple and exact objects. There is no kinematic expansion in this case. And it turns out that it's very easy to look at the SU2 structure of these amplitudes using some sort of spurion analysis in terms of the Higgs VIV. And so I can write down the different amplitudes that come in here for both a B and a W, and I and J are the SU2 indices. And it turns out altogether that there are 5 structures, because this is the only spurion that can enter in this case, this combination of H dagger tau A. Just H dagger H by itself is a singlet. So these different coefficients here are some series expansions in that, but they don't change the SU2 structure. And this turns out to actually be completely analogous to the GeoSMIFT story by these people, which involves a lot of sophisticated tools, but the amplitude just gives you a very simple-minded way of doing that. Almost done. Okay, so looking at this more closely, you can really see where these different terms come from using this on-shell Higgsing picture. And turns out that these two start at dimension 6, and the third one arises at dimension 8. So all the different structures that you have here are exhausted at dimension 8. Okay, So let me just conclude. So when written in terms of these little group covariant spinners, the amplitudes really sort of unleash the power of Lorentz. You have a uniform description of amplitudes of different spins. It's easy to see the Higgsing of massless amplitudes into massive ones. There are mature and maturing methods for the on-shell derivations of low energy EFT amplitudes. And the EFT parameterization is directly in terms of physical particles and couplings. Instead of operator basis, we have bases of kinematic spinner structures. And so this is a promising starting point for looking for novel effects. And it also gives you a clear distinction between the Heft and the Smith. So I'll stop here.
Thank you for the very interesting talk. We have time for some questions. Over there. Over there.
Is there a one-to-one correspondence between the local operators and your amplitudes, or
Yeah.
fewer? Okay.
Yeah, there's a one-to-one correspondence between the coefficients appearing in the Lagrangian and the Wilson coefficients and the couplings associated with the contact terms in the amplitude. Yeah.
Okay, more questions? Lines?
Thanks. You mentioned this resurrection of this interference effects for this. There's this 1D6 operator. It's very hard to constrain, even with the resurrection. It seems like you really have to do a combined fit of it, mixing in all the dimension 8 operators as well, because its effects are so small. Have you looked at that at all?
So first of all, we haven't really, we haven't really started to look at the phenomenology. So that's the stuff that we want to do next. The first thing here is kind of very, very simple. It's just the fact that since we're keeping the masses, there is no such thing as a non-interference. There's no orthogonal helicity structure. So it's not clear that this is going to be associated with some complicated angular dependence or something like that. But I think that the thing that would be really nice is if we can really do something to isolate a certain particular structure. Of course, this is, in the real world, things are hard, there are kinematic cuts, things are gonna, so we still don't know the answer, but the hope is that, yes, or at least that's the plan, to try to do stuff like that.
Yeah, there are a couple papers looked at it, but it's very hard to get tight bounds on it from the interference alone. You can do it at the square of the operator, and those give bigger effects, but then they're the same order in 1/λ as the dimension 8 operators.
Yeah, so I think you're right. It's not an easy thing, but that's the plan. And there's also the question of whether these writing things in terms of these spinner structures, you can work directly with them, and you have this sort of vector space of these objects, and then try to make use of that somehow.
Any more questions? I don't see any, so let's thank Yael again.